All right, everyone, welcome back. Here we are in our fourth lecture of Chapter 2, continuing our trek through the chemistry chapter. And today we are going to be looking at inorganic biochemistry. So it's a pretty brief lecture compared to that last monster that we had, but it is extremely important. The things that we talk about today will stick with us through the rest of Bio 137. It will come back in Bio 139, and it will definitely come back in your programs. So make sure to ask those questions if anything that we say today doesn't make sense. Now, as always, let's start with our not really attendance questions. And we have, what type of bond exists between the hydrogen of a water molecule and the oxygen of that same water molecule? Next, what is meant by polar? And last, what type of bond exists between one water molecule and a nearby separate water molecule? So go ahead and pause the video, try to answer those questions. Now, hopefully you've done that. Let's see what the correct answer to those questions are. What type of bond exists between the hydrogen of a water molecule and the oxygen of that same water molecule? Well, here we are looking at the bonds within a water molecule, and those bonds are covalent bonds. Now, remember last time, covalent meant sharing electrons. Nobody took anything, nobody gave away anything. They are sharing electrons. But we also mentioned that there were different types of covalent bonds. So let's be a little bit more specific here and see what type of covalent bond exists in a water molecule. Here, it is a polar covalent bond. And that brings us to the next question. What's meant by polar? Well, polar is a word that means one area of something has different properties than another area of something. So that can mean a bunch of different things, but here when we're talking about polar covalent bonds, it means that even though we're sharing electrons, we are not sharing them equally. And the water molecule has a polar covalent bond where the oxygen is more electronegative than the hydrogens. So the result is oxygen pulls on those electrons a little bit stronger than the hydrogen does, meaning that oxygen side of water molecules has a little bit of a negative charge. It's not a full negative charge. It's a slightly negative charge, leaving the hydrogen side of a water molecule with a slightly positive charge. So the water molecule itself is also polar, just like we have polar covalent bonds. And that then kind of leads us into the third question. What type of bond exists between one water molecule and a nearby separate water molecule? Here, because of the polarity of water molecules, it leads to something called hydrogen bonds. Now, the hydrogen bond, like we said, it is not just the bond between hydrogen and something else. Hydrogen bonds exist because of polar molecules. Now, usually that's because hydrogen is in one of those molecules, but it is not the bond between hydrogen and something else. It is the result of polar molecules having those slightly charged regions and slightly negative regions, slightly positive, and they are kind of drawn together, similar to a magnet, similar to what we saw in ionic bonding. Now, the reason that I asked all of these is because these are going to be a big underlying factor in what we talk about today. So let's go ahead and get rolling and talk about biochemistry. I've said that word a few times now. So what is biochemistry? Well, biochemistry is a division of chemistry that deals with reactions that happen inside of living things. It is an entire course or more to itself, so we are really not going deep at all. If you continue on into a 4-year institution, you may very well take a biochemistry class or two. So this is just kind of laying the bare bones for biochemistry. And biochemistry has two divisions. There's inorganic and organic. The difference being carbon. So inorganic biochemistry deals with inorganic molecules, and typically inorganic molecules contain no carbon. There's a little bit more to it than that, but that's the general rule, usually no carbon. Organic molecules always contain carbon. Now, sticking with organic molecules, in addition to containing carbon, they're usually large. They have covalent bonds. Remember, carbon likes to form covalent bonds. And that's things like carbohydrates, lipids, proteins, nucleic acids. That will be the topic of our next lecture. Inorganic biochemistry, dealing with inorganic molecules, that looks at things like salts, acids and bases, water. That's going to be what we look at today. So let's start with water. Water is the most abundant inorganic molecule in the body, making up about 60 to 80% of cell volume in adequately hydrated individuals. So, one thing that happens is as we age, the amount of water in our body begins to decline. When we're born, babies are lots and lots and lots of water compared to older people. Babies tend to be towards the 80% side, and older people tend to be more towards the 60% side. So water does decline as we age in our body. Water is also the most important molecule in our body, probably, arguably, the most important molecule for life. And that's because of the properties that water has. Water has some really weird properties, and it comes down to those hydrogen bonds. Hydrogen bonds allow for these properties of water to develop. So here are the 4 big properties of water that make it so important. 1, water has a high heat capacity. So what does that mean? Heat capacity is the ability of a substance to hold on to energy. When you put energy into something, how well and how long does it hold on to it? Here we're really speaking heat is the energy that we're talking about. So if we put heat into water, that water will hold on to that heat for a long time compared to other molecules. If you have ever gone to a lake or something, some other big body of water, at the end of a long hot summer, maybe you get a chilly day. First little bit of fall. You go to the water, you jump in, and the water's still relatively warm because the summer, the lake heated up, the lake holds on to that water because of the high heat capacity. The heat stays in that water, and it slowly dissipates. But it takes a while. But at the same time, it's a little hard to heat up. We're putting that water, exposing it to the heat, but the water does not get hot immediately. When you put a pot of water on the stove, it takes it a little bit to come to a boil. Next, water has a high heat of vaporization. That means that it takes a lot of energy, a lot of heat, to break water down from a liquid to a gas. So as we convert water from liquid water to water vapor, we're putting a lot of energy into it, a lot of heat into it. So water requires a lot of energy to be put into it. And actually, this is why we sweat. When we sweat, we are putting water and other things, but water onto the surface of our skin. That water is going to evaporate. Where does the energy that causes that evaporation come from? Our own body. As that water evaporates, it's pulling energy, it's pulling heat away from our body, cooling us down. Next, polar solvent. Water is polar, as we've been talking about, and that means that it is really good at dissolving things. If you put salt in water, it dissolves relatively easily because water is polar. The positive end of water pulls on negatively charged things like the chloride in salt. The positive side of water, the negative side of water pulls on positively charged things like the sodium side of salt. So it rips that salt in half. It's no longer NaCl, it's Na+ and Cl-. And then the water molecules surround those ions. When you watch salt dissolve in water, that's what's happening at the molecular level. Water is cushioning. Water acts like a big pillow. If you've ever played with water balloons and before you pop them, if you kind of bounce them around in your hand, you notice that they're jiggly. That's because of the cushioning of water. Water surrounds things in our body like our brain. It fills the inside of things in our body also like our brain. That's to protect it. That's to act like a cushion. It's to act like a shock absorber. It helps prevent concussions from occurring all the time. So those are the properties of water that make it so important to our body. And water is really reactive. Practically every reaction in our body happens either in or because of water. And there's two really important reactions that water is involved in. The first is called dehydration synthesis. The second is called hydrolysis. And really they are the exact same thing, just one is the reverse of the other. First, let's talk about dehydration synthesis. Dehydration synthesis, as we see here, we start with two molecules, each that have an OH attached to them, an OH group. If they are brought close enough together, what happens is the OH of one group and the H of another group get together, they form a water molecule, two H's and an O, H2O, and they leave. The water leaves, and what happens? Well, as the OH is removed from one side and the H is removed from the other side, it causes a positive region and a negative region of the two different molecules. They stick together. They're joined together. We'll see this in an animation in just a moment. What happens is we remove water and stick two things together. Well, removing water, that's dehydration. When something is dehydrating, water is being removed from it. When we stick two things together to make something bigger, remember from last time, that's called synthesis. So, dehydration synthesis reactions. The opposite of that is hydrolysis. Hydrolysis, we start with a big molecule, we add some water into it. The water disrupts the bonds. The water itself is split into an H and an OH. And then we split that larger molecule into two smaller molecules, adding an OH to one side and an H to the other. So that is hydrolysis. Hydro, water. Lysis is to split. So we are splitting water or splitting with water. These two reactions always happen in our body. They're constantly happening. The hydrolysis, a perfect example of that is digestion. Even though we use things like enzymes and acid, we also use water to digest. We break things down. If we want to build a protein from food that we ate earlier, we take the little pieces that we'll learn about tomorrow and stick them together using a dehydration synthesis reaction. So let's take a look at a quick video. We will possibly have sound. I'm not sure if the sound comes through in the video the way that I'm going to be playing it, but even if it doesn't, there are subtitles to the video.
Many important biological molecules are made of repeating subunits, called monomers. When many monomers join, the result is a polymer. For example, amino acid monomers join to form a protein polymer, and glucose monomers combine to form a complex carbohydrate polymer. Biological polymers form by dehydration synthesis reactions. As you can see here, each of the monomers in this reaction has a hydrogen, or H, and a hydroxyl, or OH group. In the course of the reaction, the hydrogen is removed from one monomer and the hydroxyl group from the other. The hydrogen and hydroxyl group combine to form water, and a bond links the two monomers. Hydrolysis is the opposite of a dehydration synthesis reaction. During a hydrolysis reaction, a polymer is reduced to its monomer subunits by the addition of water. In fact, the word hydrolysis literally means to break water. The hydroxyl group from a water molecule attaches to one monomer, and the remaining hydrogen attaches to the other monomer. In other words, water is used to break the bond holding monomers together. Let's do a quick recap. During dehydration synthesis, monomers join to form polymers, and water is released. The opposite happens during hydrolysis, where water is added to the reaction to break a polymer into monomers.
All right. So even if the sound did not play, we were still able to watch the subtitles there, and it demonstrated the reactions that we talked about here. So example reactions using actual molecules, don't worry about those. This is just to give an example of real molecules instead of just these individual kind of generic rectangles that we have here. Now let's change gears a little bit and talk about acids and bases and pH. So we all have heard about acids and bases. Some of us know what they are, some of us don't, but let's talk about what acids and bases actually are. Now, both acids and bases are electrolytes. So what are electrolytes? Electrolytes are things that when you put them in water, they develop a charge. So the things that we've talked about before, like sodium, if we put Na in water, it's going to become Na+. It develops a charge. So it's an electrolyte. Acids are electrolytes. Bases are electrolytes. And by the way, sometimes you'll hear the word alkaline. The word base and alkaline mean the same thing. So those two are used interchangeably. Acids and bases, or acids and alkalines, we will hear. Now, when we're talking about acids and bases, we talk about pH. And pH is a measurement of proton concentration, or H+ concentration, or hydrogen ion concentration. So what does that mean? Well, protons, H+, and hydrogen ions are all the exact same thing. You can hear any of those, protons, H plus, or hydrogen ion, and it means the same thing. Why is that? Well, we're not going to draw it out right now, but think back to when we drew hydrogen in the second lecture. Hydrogen, we drew it with an H in the middle to represent the proton. Remember, most hydrogen does not have any neutrons, so the H just represented a proton. And then the electron was found in the first shell. It has a single electron. Imagine if we took that electron away. We started with one proton and one electron. We take the electron away. What are we left with? We're left with a single proton. And how would we write that? We would write it H with a positive charge. And that's why proton and H plus are the same thing. And what would you call hydrogen with a positive charge? We'd call it an ion. So hydrogen ion is H plus. H plus is just a lone proton. All three of those words mean the same thing, and that's what we're talking about when we talk about pH. pH is the proton concentration of a solution. Why is that? Well, because acids and bases either give away or donate protons, or they accept or pull protons out of a solution. When we're talking about acids and bases, we're talking about what's happening to protons. Are we donating protons? Are we making proton concentration go up? Are we accepting protons? Are we pulling protons out of solution? Are we making the proton concentration go down? That is what pH talks about. So let's talk a little bit about acids and bases in the body before we go on and talk about what acids, bases, and pH look like, what they behave like. So the normal body pH is 7.35 to 7.45. Keep that in mind. We'll come back to it in a little bit. The normal body pH is 7.35 to 7.45. And that pH, it can't really deviate much from that. So based on that information, let's go forward a little bit. Let's look at pH, acids and bases, and then look at what happens in the body because of pH and how our body maintains pH. The pH scale actually goes from 0 to 14. We've got 1 to 14 here. It does actually go as low as 0. So the pH scale goes from 0 to 14. And there are no units. When we talk pH scale, we just say it has a pH of 4 or a pH of 12. There are no actual units. Now, when we look at the pH scale, anything below 7 is considered an acid. The lower we go, the more acidic we get. But if it is below 7, even if it is 6.9999999, it is an acid. The lower the pH, the more acidic we get. The lower the pH, the more H plus concentration we have. So pop that in your head, roll it around for a minute, because this can be a little bit confusing to some students. The lower the number, the higher the H plus concentration. 4 has more H plus than 5. 5 has more H plus than 6. The lower the pH, the higher the H plus concentration, the more acidic we are. Not only is it more H plus, each step down, so as we go from 6 to 5, from 5 to 4, from 4 to 3, each step, H plus doesn't just go up, it goes up 10 times. Not 10 more, 10 times. So 5 has 10 times as much H plus concentration as 6. 2 has 10 times as much H plus concentration as 3. So if I were to ask you, 3 has how much more H plus than 5, what would your answer be? A lot of students want to say 20, but that's not correct. We don't go up by 10 each time, we go up by 10 times with each step. So 3 has 100 times the H plus concentration as 5. 2 has 1,000 times as much H plus as 5. We go up by a factor of 10 at each step. So let's get an idea of what does an acid look like. An acid, a good example is hydrochloric acid, HCl. What makes something an acid? What does it do in water? All acids, when you put them in water, will do the same thing. They fall apart. Acids fall apart in water. We say they dissociate. An acid, like HCl, will dissociate in water. And the thing that I say makes all acids the same is when they dissociate in water, they dissociate into H plus and something with a negative charge. In this case, Cl minus. All acids dissociate in water into H plus and something with a negative charge. The more acidic something is, the more H pluses it gives off. The more H plus, the lower the pH. The lower the pH, the more acidic something is. All right, so there's our pH scale again. 0 to 14. We said anything below 7 was an acid. Now, let's look at what happens if we go above 7. If we go above 7, we become more alkaline, more basic. It doesn't matter if it's 7.000001. If it is above 7, it is more alkaline, more basic. And as we go upward, the higher the pH, the more alkaline we get, the H plus concentration goes down. Sometimes we will actually see what happens is as we go up, instead of just H plus going down, we see OH minus going up. There's a little bit more to it than that when you go on to a chemistry class, but for us, we just say as pH increases, H plus decreases, or OH minus increases. And similar to what we saw in acids, there's 10 times, but with a variation. Each step upward from 8 to 9, from 9 to 10, from 10 to 11, each step is 1/10 the H plus concentration. Each step is 1/10 the H plus concentration. So 9 has 1/10 the H plus concentration as 8. Or if we're talking about OH minus, 9 has 10 times as much OH minus as 8. That can be a little bit tricky. So let's kind of look at another real world example. An example of a base, an alkaline, is NaOH, sodium hydroxide. Bases, like acids, fall apart or dissociate when we put them in water. Here, something that makes a base or an alkaline is it will dissociate into OH minus and something with a positive charge. A base will dissociate into OH minus and something with a positive charge when we put it in water. In this case, the positive is Na+. So what's the significance of that? Well, if we put something in water that's slightly acidic, that water has some H pluses floating around in it, correct? Because something that is acidic has H plus in it. If we put an alkaline into that, what's going to happen with those H pluses? They're going to bind with this OH minus and make what? A water molecule. So alkaline will produce OH minus, and what was one of our definitions of an alkaline or a base? It is a proton acceptor. It pulls protons, H plus, out of solution. Here's how it does that. The OH minus will bind with H plus to make a water molecule, and the result was the H plus, the proton concentration of the original solution, went down. So we've talked about acids. Anything with a concentration of H plus that is high, anything that is below 7 is an acid. Anything with an OH concentration that is high or an H plus concentration that is low, if it is above 7, it's an alkaline. We've seen that when something produces H plus and something with a negative charge, when placed in water, it was an acid. Well, what happens when you put a water molecule in water? Sometimes, not always, sometimes it will dissociate. What does it dissociate into? H plus and OH minus. So when we put water in water, it gives off H plus and something with a negative charge. What does that mean? It means water is an acid. H plus and something with a negative charge is the definition of an acid. Water is an acid. But wait, over on the right side, remember the definition of an alkaline, or one of them, is when we put it in water, it dissociates into OH minus and something with a positive charge. Well, that's what happened here. OH minus and something with a positive charge. So water is an alkaline. Water is a base. Water is both acidic and alkaline. That's weird. But it's not just acidic and alkaline, it is equally acidic and alkaline. For every H plus it gives off, an OH minus is given off. It is equally acidic and alkaline, which is pH 7. pH 7 exactly we call pH neutral. 7 exactly is pH neutral. If it is at all below 7, it's an acid. If it is at all above 7, it is a base. If it is exactly 7, it is pH neutral. So we have 1 through 6 followed by however many 9s you can imagine, or 0 through 6 really. We have an acid. 7 exactly is neutral, and anything above 7 is an alkali. It's a base. So normally when we think about acids, we think they're caustic, they're painful, they're harmful. Well, they can be. Here's a pH scale with the acids at the bottom. Most of us will drink an acid on a regular basis. Black coffee is acidic. Some of us will drink wine. Wine is acidic. Most of us have eaten lemon juice. Lemon juice is really acidic. Lemon juice is pretty much the exact same pH as our stomach acid. But we'll eat a lemon without a second thought. But we also have something called 1 molar hydrochloric acid, which is extremely acidic, and if you got it on your skin, it would burn. If you put it on a table, if you spilled it, it would quickly burn. But going the other direction, bases, even though they don't get as much attention, we don't know as much about them usually until we start studying them, they can also be harmful. They don't have to be harmful. Egg whites, they're basic. But a lot of household chemicals are basic. Bleach, ammonia, lye, those are all alkalines. Those are all bases. There's our example, sodium hydroxide. So both acids and bases can be beneficial. They can both be harmful. So it doesn't really matter too much if it's an acid or a base. Bringing us back to normal pH. We said the normal body pH was 7.35 to 7.45. What does that mean? What is our body? Our body is slightly alkaline, slightly basic. I guess some of us may be more basic than others. But we can't deviate much from that. If it goes too low, that's called acidosis. If it goes too high, that's called alkalosis, and different conditions can cause that. But our body luckily has things to bring it back. Homeostasis. Remember, we've talked about almost everything in the body has a set point, and homeostasis keeps it at that set point. We get a little low, something will bring it back up. We get a little high, something will bring it back down. We have different systems in our body called buffering systems. Our kidneys help maintain our pH. Our lungs, breathing, regulates our pH. We have different chemical buffers in our body, the most important being the bicarbonate buffer system. It shows that in your textbook. You do not need to know the bicarbonate buffer system. I'm not going to ask you to draw it out or anything like that. We will talk about it in Bio 139, but for right now, it's just a good idea to know the name. So the kidneys, the lungs, and various chemical buffers in the body help maintain normal pH. Now, one thing that we see a lot are diets and fads to alkalize your body or do something to adjust your body's pH. Well, unless your body is in really, really bad shape and you're on death's door, you are not going to adjust your body's pH because our body does that itself. Our body adjusts its own pH. And if you put something in your body to change the pH, those buffers are going to bring it right back where it needs to be. All right, so that brings us to the end of this lecture. Like I said, it's a little shorter than the last one. It's not quite as intense as the last one, but there is some important stuff in here. So make sure that you understand all of it. If you have questions, ask, because it is going to come back without being reviewed in most cases. It's accepted that you understand it. So please ask those questions, and I will talk to you in our next and final Chapter 2 lecture, where we talk about organic biochemistry. All right, I will see you all then.